are our notions of dark matter mistaken, and do they have to be radically reformed? We still don't know what dark matter is.
Dark energy is...
Erik pointed out it's a very different thing. It has a name dark in the name, this is true, but it's a very different thing, has a very different effect. It pushes the universe apart, while dark matter seems to have much more structure and granularity and seems to associate itself with matter in some ways. Catherine, you measured the existence of dark matter. One might assume that she believes it exists. She does that with very new and advanced ground-based telescopes that allow her to map very large areas of the sky. And what you get out is this filament structure of dark matter that you might have seen somewhere. Then we have next to her Sabine Hossenfelder, who is from the Frankfurt Institute of Advanced Studies. She's a theoretical physicist. Is also interested in dark matter and alternative explanations for the phenomena that we see when we think they are made by dark matter. And Erik Verlinde is a theoretical physicist, and he has recently built a theory that does away with dark matter, which is a tricky business because the theory of gravity has worked very well so far, so modifying it has to be done with great care. I'll start with Erik and then go this way, I believe.
All right, so I'm not sure whether you're all familiar, of course, what dark energy and dark matter are really about. I mean, dark energy is related to observations of the fact that the universe is expanding, even accelerated, and we need then some substance that's spread over the universe that explains this. And it actually was already part of Einstein's theory about a century ago that he could add this possibility of adding a constant that made the universe expand. Dark matter is a totally different phenomenon. It has to do with what happens in galaxies and the fact there is more gravity there that keeps galaxies together, but also the formation of galaxies in the universe needs dark matter. But that's an hypothesis. And it's true that most theoretical physicists and even cosmologists and astrophysicists think there's this particle out there that explains this additional gravity, because then you can do it with the existing theory. Why would you change the theory that works so well as Einstein's theory if, well, you can add this additional component and explain these phenomena? For me, the reason to doubt this is that there's a theoretical reason why maybe Einstein's theory doesn't work the way it does. And this has to do with our insights that we have been gaining about gravity over the last century. After Einstein, we learned about quantum mechanics. We've learned more about how the cosmos works. I mean, at the time of Einstein, people didn't understand even the size of the cosmos, or the fact there were galaxies. So we were dealing with an old theory, and there are reasons to believe that it has to be changed. That comes from thinking about black holes, and even insights that come from string theory, which is a field I've been working on, tells you that simply representing dark energy with this constant of Einstein's theory and thinking about dark matter as a particle is may not be the right way. Actually, there are reasons to believe that we should modify gravity when we are dealing with the very large distances. I mean, like Einstein's gravity works very well when gravity is very strong, but in galaxies, when we are going farther out, the gravity becomes very weak, and this is where the theory may be different. And what I'd like to explain in my way of thinking about it is the connection between these two objects, the two phenomena, the dark energy and the dark matter. So dark energy is something that I believe is really there, in the sense that there is a energy in our universe that is required to explain its behavior. But the dark matter is not really a particle. It should be an effect of the interactions between ordinary matter and the dark energy. So I have sort of a mixed point of view on dark energy and dark matter, that I think dark energy is really there, but the dark matter should not be a particle, but it's some way that gravity indeed works differently in our galaxy, or in our universe, when we look at the interactions between matter and the dark energy.
Thank you very much. Maybe we go to Catherine. You measured the existence of dark matter. So do you think it is not there?
Do I think it's not there? It's tricky. I know I measured something, and we've called it dark matter, but I don't know what it is. Let me tell you who I am. I'm a professor of cosmology at the University of Edinburgh, and that means it's my job to try and understand the universe. That's what a cosmologist does. Now, if we had a bunch of professors of cosmology in this room, we could broadly split them up into two camps. Now, we'll call our first camp of cosmologists, we'll call them the smug cosmologists. And they are rightly so. Now, these are the cosmologists who have looked back to the universe as it was right after the Big Bang, and they have made exquisite observations and used that data to tell us exactly what makes up our universe today. Less than 5% of the universe is made up of the stuff that we are made up of, the stuff, the Earth and the Moon and the Sun and everything you can see. That accounts for less than 5% of our universe. Then we have 25% made up of dark matter, the strong gravitational force in our universe that binds everything together, and the rest, the other 70%, something that we've called dark energy, that appears to be causing the expansion of our universe to get faster and faster each and every day. Now, this is a beautiful theory, it's a beautiful model of our universe, and it explains the observations that our smug cosmologists have made incredibly well. There is no better theory that we have to explain these observations. And so it's an amazing testament to how far science has come in terms of technology, instrumentation, data analysis, statistics and theory, that we've come to this point of this beautiful match between observations and theory. So those are our smug cosmologists, and we pat them on the back because they've done an amazing job. Now we have our other group of cosmologists that we will call the embarrassed cosmologists, and I fit certainly into this camp. And the reason why we're embarrassed is because if you try to explain this model to anyone who's not a professor of cosmology, they look at you and they go, what? Hang on. Less than 5% of the universe is made up of the stuff we're made up of? And hang on, you've invented two things that you've called dark. And one of them you've called dark matter because it acts kind of like extra matter, but you don't know what it is. You've never seen it. You've never touched it. You just think it's there. You've invented it. And hang on a minute, you're sourcing energy out of nowhere to make an infinite universe expand even faster. This just doesn't make sense. And it is quite embarrassing to share that theory with someone. So on the one hand, as cosmologists, we're feeling very pleased because we do have this beautiful model of the universe now. But the flip side of that is it relies on these two dark entities that, to be very honest with you, we don't understand. And so, to be frank, we don't understand 95% of the universe. And you might be thinking at this point, wow, you scientists totally failed. That is an epic fail. You don't understand 95% of the universe. But I think everyone on this panel will agree that you should be looking at that in another way, because you should be seeing that as an amazing opportunity. When you don't understand something as gargantuan as 95% of the universe, it means you're missing a key piece of the puzzle. Maybe the framework that we're working in isn't quite right. And so, yes, you're right, I have mapped out the dark matter in our universe. We have some beautiful maps charting out where all of this invisible stuff would be in a framework where Einstein's theory of gravity is right. And it matches what our theory predicts. Another great example of observations matching theory. But we still haven't found that dark matter particle, and until that day comes, I remain the observer sitting here, and it's my job to test the theories that people like Erik and Sabine come up with and try and disprove them.
Sabine, dark matter, dark energy. He believes dark energy exists, certainly.
Okay, so I'm a theoretical physicist, and my task is to come up with explanations for what the astrophysicists find. Preferably some simple explanations, because if you have a lot of parameters, you can fit pretty much everything. So first I would like to object on this idea that it is embarrassing that we can't explain 95% of the universe, because this 95% is a totally meaningless number. The point is that these 95% are really, really simple. At least on cosmological scales, we can describe them with one parameter for each. There's the cosmological constant, and there's the average density of this dark matter stuff, and that's pretty much it. So I would agree that this is a nice and simple theory. The problem is that if you look at galaxies, and Erik already said that our best observations about dark matter and so on come partly from the galaxies, then it's not quite as simple. You actually have to do some work to get these galaxies to work out properly. The thing is that you can do it with dark matter, because this is stuff that is distributed somewhere in the universe, and you can put it in the right amounts wherever you need it. So if I give you any galaxy and you have to explain what you see there, you just put the dark matter where it has to be in the right amounts, and then you call this an explanation. So now, from the perspective of a theoretical physicist, that's a little bit unappealing, in particular because if you look at the structures of galaxies, they have a lot of regularities that are really, really hard to explain with this hypothesis of dark matter. One of which is, for example, that the amount of dark matter in a galaxy, and not only the amount, but also the distribution, seems to very closely track the amount of visible matter. And you can make that work with particle dark matter. You can't calculate it on a paper, but you have to do fairly complicated computer simulations. And after they've been twiddling with these simulations for 20 years and added a lot of parameters, they've managed to produce some galaxies that look like what we actually observe. Now, on the other hand, there are various theories that modify gravity, from which Erik's theory is one. And they managed to get these regularities out basically in a two-line calculation. And I find it very hard to believe that there is not something to it. So now I want to answer specifically the question that you had here. Are our notions of dark matter and dark energy radically mistaken? So I've taken offense with the question because it's not our notions that are mistaken, it's everyone else's notion that is mistaken. My notion is the correct one. So I have this idea that it is actually a mixture of dark matter and modified gravity, in the sense that it is some kind of particle that sometimes behaves in a way that looks like it modifies gravity.
So it is a particle, which gives me, as a particle physicist, hope that maybe I can still build detectors that find it. But let us go back to Erik. You have basically removed the need for dark matter, and Sandra just said that in her view of dark matter, it is not a simple element. It has, you can distribute it however you want to make the theory fit. You have many parameters after all. So is it so then that we don't need any dark matter? And extend this question, what about the other mysterious darkness in there, the dark energy? Can we either get rid of that or incorporate it into a nice theory where it emerges in a sensible way?
So, as I mentioned already in my first opening remarks, is that I think there's a fundamental difference between adding dark energy or dark matter. Dark matter is assumed to be a particle very much like the particles we are made of. Dark energy is this other mysterious stuff that we don't know what it is. I believe that we have to first of all explain all of these things and not just one without the other. And for me, the dark energy is something that I think means that we have some mysterious component of energy in our universe, so that our universe is not really in its lowest energy state. We have sort of added some there, and we have to explain this. And so I think our current theories are clearly not enough to describe what dark energy is. But I think when we understand that, we can also explain those phenomena that we now attribute to dark matter, and then we don't need it. But that doesn't mean that I have already the theory completely ready there. I mean, I made some calculations that could explain what happens in galaxies, those regularities that Sabine talked about. Those regularities come out of this idea. But there's another role for dark matter, which has to do with this early universe, explaining what happens in the observations of what is called the cosmic microwave background, or the way that structure forms. And so these cosmologists that are using dark matter to explain all these phenomena very precisely, they indeed use very specific ratios of these things to explain this. I have to do still the same thing. I mean, there's some work for me to be done, but then I have to do it without adding this dark matter. And so this is a challenge still. I mean, the theories are not complete yet, but this is where I think indeed the fact that we have this mystery out there is, for a theorist, an ideal opportunity to solve these problems. And it doesn't always mean that those solutions are already the first one that people thought about, like adding dark matter. It may be a different way. And for me, it's indeed trying to understand gravity better and then explaining all those phenomena. But dark energy for me would be an element actually that should be added. And maybe I should mention this. I mean, I have many colleagues in string theory that are working on a universe that does not contain dark energy, or even have the opposite sign of what we call the dark energy, namely a negative cosmological constant. That's a mathematical universe that doesn't look like ours, but they can understand gravity very well there. So I have to take those people and motivate them to also work on this universe that does have dark energy in it, in the positive contribution. And I think that is a very important component of our universe. We have to take that seriously.
So will we be able to make a mathematical universe that matches the real one, but means that it has a positive dark energy and an expanding universe, with your model where you take the dark energy as there, that's how I understand it, and you have essentially gravity itself emerge from something I don't understand. But we just shouldn't talk, just the two of us. First, maybe I go back to Catherine. He can explain how galaxies move in this model, it seems. Can he explain how you're measuring dark matter by measuring how slight deviations of light going all the way through the universe, how light's slightly deflected by the mass, by the gravitational pull of dark matter, which is not quite the same as sort of thinking of galaxies moving around each other, or stars moving in galaxies, which is the most famous evidence of dark matter. Does it work?
Does it work? So Erik and I actually have published a paper together. We were one of it was one of the first papers that tested your theory. And let's take a little step back. So how do we actually see this invisible dark matter? So I said I've mapped out this dark matter. You're probably thinking, well, if it's invisible, how the hell has she mapped it? Well, what we do is we look at very distant galaxies. Light travels through the universe for about 7 billion years. And as that light travels through the universe, it doesn't travel in a straight line. Its path gets twisted and pulled by the gravitational pull of all of these invisible dark structures around it. And so what we do is we spend a lot of time on remote mountaintops, far away from all of the light pollution in cities, and we take very, very deep images of the universe, collecting all of this light from these distant galaxies, and then we interrogate that light to tell us about its journey, its 7 billion year journey from that galaxy to our telescope. What we can do is we can work out how its light's been bent and distorted by all of this invisible stuff that's out there. Now, you said, does dark matter exist? I know that something's there. I know that there's something that's curving space and time, that's distorting these images of the very distant universe that I map out. But I don't know what it is, but I know it's there. And what we did when we tested Erik's model was we said, okay, what would it predict for the gravitational pull around galaxies? And when we started working on it, I was like, this is never going to work. This is going to be great. We're going to disprove this theory in a week. Unfortunately not. Margot, who was leading this analysis, she was a fantastic PhD student in Leiden at the time, came up with these results, and she compared our best model of what dark matter should be with Erik's theory, and found that it fitted our data equally well. So both theories fitted our observations equally well. And but what was important, and this is what Sabine was saying, was that this new theory requires, we say, no free parameters. So a parameter is something in your theory that you can use to tweak and turn the knobs to boost the theory or lower it. And there's no free parameters in this theory. And that was very motivating and supportive of this theory. But I think, Erik does, and team and collaborators, and indeed you've written a paper extending this analysis, this theory as well, and I think that's where we need to be going, because I would love the particle physics experiments to actually catch a dark matter particle, or I'd love someone in CERN to create a dark matter particle, because then that piece of the puzzle would be done. And maybe that's just around the corner. CERN's going through an upgrade. It's going to be colliding particles together much faster with much higher energies than it's ever done before. Maybe that'll be enough to create a dark matter particle, the simplest theory that we think is out there, and we've got that bit solved. But until that happens, I think we've got to investigate new theories.
Sabine, you investigate yourself new theories, taking some of Erik's ideas, I understand, and your own. And as you mentioned earlier, in your favorite model, there is still a particle in there.
Yes, at least you could interpret it this way. So I have not written a paper with Erik, but I read the paper, or I tried to read it. And while I was reading the paper, I was reminded of a passage from Steven Weinberg's book, Dreams of a Final Theory, where he describes that there are two types of theoretical physicists. There are the seers and the mystics. And the seers are the ones who make an argument straightforwardly, go from A to B to C, and everything, one follows after the other, and you can very easily follow their argumentation. And the mystics, they assemble a cloud of facts which they lay out, and then a miracle happens, and out comes the result. And I think that Erik is definitely of the second kind. And I had a hard time making sense of the paper, so I set out to try to put this into a more digestible form. And I found, interestingly, two things. One is that he says he needs to start with dark energy, and then dark matter is a consequence from this. So I find that if you try to write it down in a rigorous mathematical way, you actually get both together. So you do not need to start with assuming that dark energy is there, but they are both parts of the same story.
Erik, did you not write it down in a rigorous mathematical way? Is there something you need to fix?
There's a starting point. I mean, I mentioned this, that if you want to really make things mathematically rigorous, we haven't found a model yet for our actual universe with positive dark energy. The people that are working in my field have to work in this fictitious universe with a negative cosmological constant to be mathematically rigorous. But mathematical rigor or very medical precise things can sometimes be even too constraining. So I laid out a number of ideas and assumptions, and from there on I started reasoning, I think, mathematically precise, in the sense that the steps are mathematically precise, but I have to make also some hypotheses in there which I motivated from a certain intuition. So physics cannot be started from no assumptions at all and then just reasoning. You have to make some hypothesis and then continue, and then that's what I wrote down is mathematically precise, but it's based on certain assumptions.
Now, one could be forgiven for thinking, okay, 20 years ago we could have had a very similar debate. Not quite the same, we didn't have Erik's theory, for example, 20 years ago, but nonetheless, there was evidence for dark matter, cosmological evidence based on the fact how light bends under gravitational influence, and also already somewhat, we didn't really touch on it very much, on dark matter evidence and cosmic microwave background and early structure formation of the universe, which also touches onto the dark energy side a little bit. So why haven't we moved on? Sabine.
Yes, I'm happy to say something about it, but I feel like I should add something here, because I think that some of you might be missing a piece of the story, because up to now you might have gotten away with the impression that Erik's model actually explains it all, so why are we even discussing this? The point is, of course, that it does not. There are some observations that at least it presently cannot explain. For example, the structure that we see in a cosmic microwave background. This is just something for which particle dark matter works very, very well, but that at least presently cannot be explained with modified gravity. And there are also some problems with other observations. So this is why there is still a debate in the community, right? So just one ought to be on the same table. Now the issue about why we haven't made progress, one of the reasons why this hypothesis of particle dark matter became so widely adapted was that 30 years ago or so, theoretical physicists had a lot of other reasons to believe in the existence of additional particles that, conveniently enough, also could make up dark matter. For example, there's an extension of our current theories that is called supersymmetry, in which you get a lot of additional particles, some of which just have the right properties to make up dark matter. And this certainly lends a lot of credibility to this hypothesis. Now, people have looked for these particles since the mid-'80s with increasingly higher precision. Have built larger detectors and better apparatuses, and they haven't found any. And now the most recent round of experiment just concluded, and I think there's now, some sense in the community where people are asking themselves, how far do we really want to push this? Like, do we want to continue building larger and larger detectors forever, trying to hope to find this particle which may not even be there?
Now, as a particle physicist, we would probably not say we have concluded quite yet. I mean, the next generation of dark matter experiments should increase the sensitivity by a factor of 100, so that's quite a distance to go. But Catherine, as a fellow experimentalist, do you think we have made no progress? And if so, why?
It's always an interesting interplay in science between theory, experimentation, and instrumentation. And it's sort of like what drives what. So normally, the way it works is kind of a loop. A theorist will come up with a really awesome theory, and an observer or an experimentalist will design an experiment to go out and test that theory. And that may require innovation, new technology, that will eventually feed back into a wider realm. But they'll test the theory and they'll find something new, which will stimulate another theory, which will stimulate another experiment, more instrumentation, and so on and so forth. And I think, you say we haven't moved on, but actually this is a really short amount of time if you want that loop to work. So what I'm very excited about at the moment is next year we are going to be opening a brand new telescope in Chile, again on top of a beautiful mountaintop high above the clouds in a very, very dry region. It's called the Large Survey Synoptic Telescope. And we're going to be imaging the entire night sky every 3 nights. We're going to be building it for 10 years. So absolutely massive telescopes, one of the largest telescopes that's going to be working on the ground. And we're going to be building up the deepest image of the universe yet, which allows us to confront a whole range of different theories. And in doing so, it will stimulate theorists to come up with even more theories. I mean, it was only very recently that it was when I was at university, so 1998 was when the first evidence came about for dark energy. Now, that's very recently, and it's only now, well, next year, that we'll have the instrumentation ready to really robustly test these different theories.
Sabine, you also, in your blog and your publications, hint that you think maybe the way we do science, the scientific or academic process, might be holding us back in finding new and unconventional theories. Can you comment on that?
Yes, I will just latch onto something that you just said, that if you get new results, quite possibly null results, then this will stimulate theorists to come up with new theories, which is undoubtedly true, because the theories that they now have, they can always be adapted to accommodate a null result. And actually we have a huge amount of theories for particle dark matter already that can eternally be adapted. Mm-hmm. And that's very convenient if you're a theorist, because these are basically theories that cannot be ruled out. Now, you were talking about this virtuous cycle in which experiments go out and they find some evidence and that guides the development of new theories. But the problem is that null results are very bad guides. They tell you very, very little about the new theory that you hope to develop. And that risks that we end up in a vicious cycle in which the null results do not lead to better theories, so we get stuck with the theories that were not good to begin with, which stimulate further of the more experiments will lead further null results, and so on and so on. And personally, I think we've been stuck in this cycle for some while already. And one of the reasons is that theorists, I think, a lot are actually quite comfortable with theories that cannot be ruled out. And now the great thing, I want to emphasize this again, is that Erik's model, at least in the way that's in the paper, doesn't have any free parameters. So it is in principle very easy to rule out, and that's quite a daring thing to do.
So,
Can I just come
yes, please.
very
Go.
briefly?
Yes.
This is the beautiful difference between astronomy and particle physics, though. When you design an experiment for particle physics, it's to answer one question. How much money do we spend on CERN? Fabulous. CERN is fabulous. I love it. It discovered the Higgs boson. Fantastic. Hasn't found anything else yet, though. So this wonderful telescope that I'm talking about, not only are we going to be able to test theories about dark matter and dark energy, we're also going to be mapping out all of the killer asteroids that might one day obliterate planet Earth. So don't worry, guys, you are safe with astronomers looking after you all.
Reassuring. I would argue that we found things at CERN, actually, interesting ones, but not yet a new particle. New composite particles, but not new fundamental ones yet. And certainly nothing that really contradicts the standard model and allows us to distinguish the standard model from possible new physics models with new particles in them. Some of them could or could not be dark matter. Does your model allow us to make such a test? Can I go somewhere, either to Catherine or to CERN, and say, your model contains an element that allows me to distinguish it from the standard mainstream theory that dark matter is a particle?
Well, that's certainly the idea, is that when you develop the theory and you understand better, that you don't have all the free parameters that allow you to explain every observation. So eventually you want to have a theory which has particular predictions for, well, things that you can observe. And I think those observations will not be here on Earth. They're mostly the kind of things that Catherine is doing, where you look at how dark matter is distributed around the universe and how it is behaving, at least effectively. I mean, this extra gravity that we see, how that's behaving. You want to make predictions for that, and then you can test these ideas. And so I feel the reason why we didn't make a lot of progress is that those observations were not precise enough, and we had these crude models that could be adjusted by so many parameters that they seem to be consistent with everything. Having more precise observations and more situations where we see dark matter really directly what it's doing, then a theory becomes also more testable, and you can exclude a theory if it's not a theory that has all these adjustable parameters. You want to have a theory that has a logical framework without being just too flexible.
Yes, but to push you a little bit further, what we really like as experimentalists are theories that make predictions. So before the data from the LSST are there,
that's right.
That make predictions that then can be tested after the data arrive. Have you got any of those?
No, but I think that this may be a very beautiful time where theory and experiment are working together. I think in understanding nature, it's not like the theorists have to be locked up in one room and the experimentalists in the other one, where the theorists come out and now they say we have something, and then the experimentalists say let's look at this and then test it. No, there can be exchange. And it doesn't mean that the theories are developed to explain exactly only the data, but they can give hints of what direction to go into. So I think the reason why we didn't make a lot of progress may also because we had not enough data to even guide us in the right direction. The problems that we are having may be so complicated is by sitting in a room, you may not just find the solutions. You have to also be able to see what you're trying to explain.
This is a notion that warms an experimentalist's heart very much, because I also believe that data is, of course, the crucial element to make progress. So as a last theme, let's look again at your theory as an example. It's a very radically new theory in many ways. I mean, as I mentioned, touching gravity is something many people have tried and usually burned their fingers because it is a very successful theory already. Will the development of such a radically new theory also give us insights beyond dark matter? Will it change our view of the universe? Maybe also in a way that one day I can find new particles at CERN, which would be nice.
I understand that that's one of your motivations, but I think the issue was already raised. Dark matter is also needed to explain what's happening in the early universe. We want to understand where all the structure comes from. And if we start understanding gravity in a different way, we may have a different explanation of those same phenomena, and even have a different story to tell about how many of these things arose. I mean, I'm not very happy with the current way and we have done this. If we think about how we extrapolated the current theory, using Einstein's equations all the way back, we have made many assumptions, and I think that story may change. But I think it's a general fact that certain theories eventually will be replaced by the next one, where we can explain more phenomena, and sometimes it's not even easy to predict which phenomena can be explained in advance. I mean, you have to first go through the steps of developing the full theory. And actually, I'm not doing this by myself. In that sense, and maybe I should even make clear that I'm not only inventing a new theory. There are many theorists thinking now about changing the way that we think about gravity and trying to derive it, think about it as an emergent force where we start from a different language microscopically. What my colleagues are not seeing yet is the connection with the phenomena associated with dark matter. But the fact that we have to think about gravity in a different way is being done by many other theorists at the same time. So I think it's just a matter of time before that theory is developed, and hopefully not by myself only, but by a group of theorists working on this problem.
Science is a collaborative process.
That's right.
And not one where single heroes rule. I very much like to hear that. And it is collaborative amongst theorists, amongst experimentalists, and clearly between theory and experiment. Sabine, what do we need to do to get a better theory of everything? Let's not go for small things. Everything. The universe, her universe, my universe, everybody's.
Well, I do think that dark matter is a good place to start with, because in this case, at least we know there is something there. I mean, we do have some observations, which cannot be said about other problems that people have tried to solve in the foundations of physics, where they worry that their equations are not beautiful enough, like this search for unified force that unifies the interactions that we have, and that may exist or it may not exist. So I think that dark matter is a good place to start with, but you were asking about what else can we learn from it. So there's an interesting thing about Erik's approach, which is that it tries to make contact to a possibly underlying structure of space-time. So the way that we currently deal with space-time in our theories is that it's primary, it's fundamental, it's just there. But there are some approaches that try to give quantum properties also to space-time, which are generally collected under the term quantum gravity, of which string theory is one example, that posit that maybe there's something more to it. And one manifestation of such an underlying theory could be something that looks like dark matter. So indeed, finding dark matter and finding out that it is maybe described by a theory of modified gravity could also tell us something about this underlying structure of space-time, which would really be very, very exciting. And for me, it's also one of the motivations to work on that.
Thank you. Catherine, what do we need to do?
What do we need to do? Big telescopes.
Big
Preferably
telescopes.
up in space.
Yeah.
My ultimate dream, if some really rich person is out there, I'd really, really, really like a liquid mirror telescope on the dark side of the moon, please. I think that would be really awesome. You could carve out one of those craters, have it on the dark side of the moon. The bigger the telescope you can get, the more information, the more light you can collect, the further back in the universe that you can see. And with more data, more information, we can really test all these theories and really find out the answers. I always think of sort of our job as astronomers, looking back in the past, we wanted, our civilizations wanted to explore the Earth, and I think what we need to do now is explore the universe, and to do that, really big telescopes are the way you want to go.
Big telescopes are wonderful. If I have my personal wish, I want big detectors. Not out there on the moon, but down there, underground, so they're not disturbed by all these cosmic radiation and all these things, to see the dark matter particles that might or might not be there. And anecdotally, rich person, the next big thing of this kind of detector will be built in the Sanford Underground Research Laboratory. And Sanford was indeed a very rich man who made his money with credit cards. So I don't know how many families he ruined in the process of that, but this lab is actually partially funded by somebody who's I fancy my own lab. I think we are sort of moving slowly towards the end of this. The audience should start thinking about their questions while I'm making my microphone somewhere go where it should go. And what we need to make progress is more data,
More theories.
collaboration, more theories. More theories?
Well, yeah, maybe I should add something there. I mean, many of my colleagues are indeed thinking about a universe that's not like our own, and they're more motivated by the mathematical consistency or the beauty of their theory. And I think we should also motivate them to get out of their room and contact and talk to
Theories that have
experimentalists.
to do with reality. Let's go for those.
And
yes.
then, if a larger community works on this, I think this is the way to make progress. I think that's a very important element. Otherwise, it will not happen.
Indeed, there has been a little bit, and I think that's one of your concerns, there's been a motion towards theories that are a little bit disconnected from reality, which are very beautiful and very nice, but mainly mathematical and not so much physical.
Well, I agree with that point of view.
Yeah. So something to agree on. Actually, many things to agree on.
Yeah.
We mostly agreed broadly. It's time to wrap up now. So thank you very much to the audience, and thanks to all our panel members for a very interesting debate and for answering all these questions. Thank you very much.